Okay, so I'm going to handle the next couple of problems together. The purpose of these problems is just to make sure that we're all on the same page with respect to concepts involving forces, particularly Newton's first law. So the first problem involves a spaceship which is sitting still on the launch pad. Ignoring rotation of the Earth, which was just added to make sure that anyone who wanted to overthink the problem knew not to. Ignoring the rotation of the Earth, draw it, using arrows to indicate all the forces on it. So, let's talk about what's happening with this spaceship. It's sitting still on the launch pad. Its velocity is 0. That's not so relevant. The main issue here is that its acceleration is 0. Because its acceleration is 0, you know that there has to be no net force on that spaceship which is sitting on the launch pad. While it's sitting on the launch pad, we know that we have a force of gravity down on it. If that was the only force on it, of course, the spaceship would be, according to Newton's first law, accelerating downward at a rate which was proportional to the force and inversely proportional to the mass of the spaceship. We know that the spaceship is not accelerating downward, so we say that there is something known as a normal force, which is opposite in direction and equal in magnitude to the force of gravity. The normal force is something that we'll discuss more in Thursday's lecture. Two things I want to point out about this drawing, however, is that I've drawn the force of gravity as being centered, more or less, ignoring my inability to draw, centered more or less in the spaceship. The normal force I'm drawn as arising at the point of contact between the spaceship and the launch pad. So you know that these forces have to be present. Well, gravity is present because I haven't said it's not, and the normal force has to be present because the spaceship is not accelerating, so you know these have to cancel each other out. There are no forces in the horizontal or, for that matter, any other direction. Shifting over to number 2, now we have a spaceship sitting still on a launch pad. Once again, sitting still is your cue to know that it has 0 velocity, but more important, it has 0 acceleration. Now, for some strange reason, our planet has no gravity, so we no longer have that vector, force vector downward. And because there is no gravity on our spaceship, we also have no normal force. If you were to draw in gravity, were to draw in a normal force, but not drawing gravity, that would mean that there had to be a net force on the spaceship going in that direction, and the spaceship would in fact accelerate in that direction. That's not what's happening, so we conclude that there are in fact no vertical forces on the spaceship, nor their horizontal forces. One of the reasons why I introduced this problem was to make sure to point out that in the absence of gravity, we do not have things floating off. That's the common vision. The idea is that, oh, if gravity were suddenly turned off on our planet, we would all suddenly start floating off into space. That's not true. If gravity were suddenly turned off, then as long as there was no force on us in the vertical direction, particularly up direction, we would not go floating off. We would simply remain on the ground until we, for instance, tried to walk, pushed off with our foot, and then we would head off in whatever direction without having any reason to fall back down. Good thing nobody is turning gravity off. So finally, let's look at the third of this trio, number 3. Now you have a spaceship coasting along. I've drawn it in the horizontal direction, but because it's in the middle of space, it doesn't really matter. It has a velocity now of 50 meters per second. It's in deep space, far from any planets or stars. I've added that portion of the problem to indicate that there's no gravity of any sort that, or any relevant gravity that's acting on it. We'll find out on Thursday that gravity acts everywhere, but we can consider it to be sufficiently weak as to be non-existent on this spaceship. Its velocity is constant at 50 meters per second. It will continue at 50 meters per second for eternity or until it runs out of universe, whichever comes first. Its acceleration is 0. When we see the acceleration equal to 0, we know that the net force on our spaceship also has to be 0. Notice that I've drawn no force vectors at all on the spaceship. I could, however, have drawn force vectors in any direction as long as they were balanced off exactly. As long as their vector summed to 0, and I'm going to cross those out because there's no reason to consider them to be there, but as long as their vector summed to 0, then the net force would be 0, the acceleration would be 0, which is the case for this spaceship.